First of all, thank you for giving me this opportunity to speak in front of all those young people. We didn't consult with Mathilde, but I will be speaking also about transfer learning. But I will adopt a different viewpoint, I think, and I will try to make a relation with parallel transport and say that maybe we could, or maybe even we should make that relation. Okay, so first of all, induction in general is about using information from some source data to some expected queries. If we first, so there are two questions, of course. One is which link between the source and the target we are ready to make. And the second one is, of course, what kind of guarantees can we look for in this case. So first, we will look at supervised induction, the classical setting. In the classical setting, you know that we have some distributions, we have some training data, we have some expected queries, and we have the same, it is assumed that we have the same training, same distribution for training and testing. And if we have this assumption, then empirical risk minimization is the way to carry on. And you know that if you have a good hypothesis on the training data, it is expected that you should get a good hypothesis also for the testing data. And we have that kind of guarantees that you see here, where, of course, you have the number of training data which is here, and you have also some assumption about hypothesis space, okay? And so you have a relationship between what is expected as a performance with respect to what you got on your training data. Okay, now, in order to do that, you have to have a bias, otherwise it doesn't, otherwise your bounds are void, and you have what is called a representation bias, which is about the hypothesis space that you are ready to consider. And you have also search bias. We don't speak much about that usually because we don't know how to do something with it. But you start from some hypothesis, and then, for instance, with stochastic gradient, you explore your space. So this is the classical setting. Now, if maybe you know also about semi-supervised learning, where you have some training data which is labeled, usually a small set of data. And then, of course, from this small set of data, for instance, you will learn something like that. But if you get a large amount of unlabeled data, such as those ones here, then maybe you're ready to reconsider your former hypothesis here and to go to that one, okay? It seems reasonable. But in order to do that, you have to make some assumption about the relationship between the distribution of the unlabeled data on the distribution for the labeled one. On Px, the distribution on the input data, and P of y given x, the concept distribution, if you like, or the conditional one. Okay, so usually the prior assumption is that the decision function should not cut through the high density regions of x. Okay, and if so, this is an assumption which makes a relation between Px and Py of x, Py given x, okay? And if you make that assumption, then you can have that kind of theorem which says that, again, you can bound the risk of your true risk with respect to the empirical risk if you have enough labeled data and unlabeled data, okay? I don't want to enter the details of the proof, but just to say that we have that kind of guarantees that I call lamppost theorems, because those theorems, those guarantees, say that if the signal presents the properties that we assume, then if the learning method, given enough data, will find the correct or something which is close to the correct hypothesis. And I call that lamppost theorems because this is like if your key is below your lamppost, then you'll find it. You're guaranteed to find it. Otherwise, you have no guarantee. And we cannot do better than that. Okay. So now, what about out of distribution learning? Of course, it seems that, as was said by Mathilde, it's much more difficult. So I will look at several out of distribution scenarios. And we will look what happens for all of those ones. So the first one is learning using privileged information. I don't know if you know about it. I will look about it. Then domain adaptation, I will just skip about it. The concept do it also. And then I will go over transfer learning. So learning using privileged information is a scenario that was invented by Vapnik in 2009. And he was inspired by learning at school. He said, OK, when you learn at school, you are given a lot of information that that won't be given to you when you are on the test, in the test room, okay? So, for instance, suppose that you have the classical task of learning an hypothesis, given some data. Suppose that you have additional information here during training that you won't have during testing, okay? Another question that Vapnik asks is, can we then improve the generalization performance with respect to the ones that we would obtain if we had only this information during training, okay? So we have some kind of additional training, additional information that we won't have at testing time. Can we use that to help learn a good hypothesis? Okay, well, it seems very strange. I agree with you. So here are some examples. So you have an image, and a teacher will say to you, okay, black, white, brown patches, and so on. All those features are important. Or you have another image in the center there, and someone will make a bounding box around something. Okay, or you have some text about the images. Okay, so those are additional informations that you have during training that you won't have at test time. Okay, I skip that. Domain adaptation, we already saw what it is. So for instance, you are trained on high quality data and then you are tested on low quality ones, or you have images in the daylight and you want to be tested on images that are not in the daylight. Concept shift, I won't enter much of the detail, but it's about then you have different distribution, the conditional distribution, for instance, spam detection for different users. For instance, a conference announcement are interesting for me, but not for my children. So their spam detector could be different. And transfer learning, I will say that it's more general than that, because your input space and or your output space could be different, okay? I will go back to that later. So learning to play chess, for instance, while you have learned already to play checkers, is an extreme case of transfer learning, at least for machine learning now, but we do it all the time ourselves. We are doing that kind of transfer learning. Okay, so let's go back to the two questions before. So which link between the source and the target, and what kind of guarantees can we look for? Let's go back to LuPy, so the Vapnik scenario. So he said, okay, his hypothesis, his assumption, the prior assumption that you need to have is to say privileged information will allow us to identify hard examples with respect to compare to the easy ones, okay? And if we are able to, in fact, filter out hard examples, then we will only keep the easy ones. And if we do that, okay, I skip the algorithm, but if you do that, then you go from the non-realizable case with a slow learning rate to the realizable case where you need less data in order to find your hypothesis. So it has always been the obsession of Vapnik to go from the slow learning rate to the rapid one. And if you remove the hard or confusing examples, then you can go back to the realizable case, which is you know that your target function is inside your hypothesis space. Okay? I don't want to enter more than that because it's just an illustration for me. Okay, now transfer learning. So we saw with Mathilde that there are some approaches to transfer learning. One, which is very classical, is to use part of, you train your neural network on a task A, and then you use part of these neural network, the first layers, in order to solve the second task. That is, you have another another neural network here, but you keep the first layers because you assume that the features that were learned for the task A could be useful also for task B. Okay, so you have just to learn that part and maybe to fine-tune the whole neural network. Okay, so this is a classical approach, which is in the middle between model-based and feature-based approach. So anyway, this is a good way usually it gives good results when you do transfer learning. But of course, you have to note that here, usually you have exactly the same input space in both cases. Okay, so this is a nice way to make transfer learning. Now, what kind of guarantees do we expect, or maybe no, what kind of parameters should play a role in the guarantees that we expect for transfer learning? What would you say? What are the ingredients for such theorems? What do you expect? Do you expect, for instance, that the distance between the source and the target task play a role, but how do we measure that distance? Do you expect that, so maybe the quality of the source hypothesis? Does the source hypothesis has to be good on the source task in order to have a good hypothesis on the target task? What do you think about it? Do you think so? Do you think to be a good checker player to be a good chess player or not? Well, anyway, that could be an ingredient. Usually, it is an assumption that you have to have a good hypothesis on the source task in order to have a good hypothesis on the target task. Okay. Now, the distance, of course, between the two tasks should play a role. But how do you measure that? You expect that the smaller the distance, the better the transfer. And of course, the number of training data points is important because if you have enough training data points in the target task, you don't need to make transfer. Okay? So I suppose that at least those three ingredients should play a role. All right? So we will see in the remaining of the talk if this is indeed the case. Okay, so now I will make a side step and talk about a little bit about parallel transport and the covariant derivative. So first of all, what they are, it's very simple. So first of all, let's go to the Euclidean geometry. In the Euclidean geometry, it's very simple. If you add two vectors, u and v, you get u plus v, no problem. And if you want to compute, for instance, a derivative, you have to make the difference between two vectors, the vectors at s plus epsilon minus the vector at s, and then you divide by epsilon, and you have your derivative. Okay? But in order to do that, you have to transport your vector from s plus epsilon to s. Otherwise, you cannot do that operation here. All right? And in Euclidean geometry, there is no problem about that because you have the same referential everywhere on the space. So no problem. Now, if your space is curved, this is no longer the case. You have non-Euclidean geometry, then your space is covered with different referentials, and then it's not easy. It's not you cannot do that without precaution to compute the difference between two vectors when they are not taken at the same point, because it is not the same referential. So in this case, you have to resort to what is called the covariant derivative. And I won't enter the details, but in the covariant derivative, so you see the idea is to transport a vector parallel to itself. And you do that using such this equation over there. I won't enter the details of it, but this is the definition of the covariant derivative. And it is, you have two parts in it. You have the classical derivative here, and you have something which depends on the way your referential is changing in the space. Okay, so you have to have the two parts, and you have to realize also something which is the parallel transport is path dependent. That is, if you transport this vector this green vector here parallel to itself, then along this curve here and back here, you see you don't have anymore the same vector. Sylvain Chevalier, for instance, would explain that much better than me. and anyway, so it depends, this difference of the vector depends on the path that you have traveled during your parallel transport, okay? And this, you find it also, I mean, we should find it also when you do transfer learning. For instance, you have your hypothesis on the source task here, you have your target task here, and if you go through an intermediate task here, you should maybe see that the hypothesis is not the same. Okay, so parallel transfer learning should be also path dependent. Okay, and in fact, if we look at something which is very common, which is analogy, analogy is some kind of very simple and also very complex transfer learning. If you ask people to solve that analogy problem here, you will get a distribution of answers here. But if you ask the same people with this question, with this task here, that is first to solve that and then that, and you don't give them any answer here, it's very striking because you don't get at all the same distribution of answer here. So it is really path dependent. It's not the same here and here. So what I want to stress is that transfer learning is like, I mean, you could make an analogy with parallel transport. My claim is that we should all, as a community, look at transfer learning like a parallel transport of an hypothesis over the space of tasks. And if we do that, we should, of course, find phenomena like that, which is path dependence. Okay, so my claim is thus that transfer is parallel transport of the source hypothesis, and I will just look very quickly on several attempts to do that in machine learning. The first one is what is called tracking, and this is from a paper of 2007 by Sutton and his colleagues. And he said, okay, instead of learning a complex learning function over the whole of the space, here, if you know that the task is slowly evolving with time, which is your queries will be slowly evolving with time, then you don't have any longer any interest, any profit to try to learn that complex function here. You should try to learn smaller, very simple ones, and just to adapt that along the time, because in that way, you can learn from less data than if you try to learn the complex dependency. And you can be much better. Actually, they did that for Go playing. And they showed that doing that, they are better than Go systems that learn from the whole of possible positions. Okay? So you learn from your current position. And then you know that your position will slowly evolve. And you should not try to get a good evaluation function, a good overall evaluation function, but just one that is slightly evolving like that. And so they have a learning algorithm to do that, which is very efficient. And they show that with less data, they are better than systems that try to learn an evaluation function, which is good for everything. Okay, so the thing is that they learn features here, and those features are weighted, so they have a set of features. And they show that these weights will evolve with times. So they will be specific to positions. And with that, in that way, I won't enter the detail, but they show that, for instance, in general, it's better to have a position to put your pawn here. But if you are in this situation, it's better to put it here than here. And with their system, they can find it. While if you try to learn from all the positions, you won't find that. Okay, so in a way, it's like if you have the space of task or Go positions, you have your features here with weights. And for one task, you have a set of weights. For another task, you have another set of weights. I'm showing you that now because I will reuse this later on. Okay, I think I will skip rapidly. Yeah. The computer vision example. So I just want to tell you that in computer vision, of course, the space is continuous. And it's very easy to have, more easy to do parallel transport in that space. And for instance, you have this very interesting paper here, which shows that convolution, the convolution operation in neural networks should be transported with parallel transport if you want to apply the same convolution, for instance, here. Well, you change it given the curvature of the figures that you are trying to look at, and you can do that very efficiently with parallel transport. Okay, I will skip curriculum learning. Just curriculum learning is trying to find a way to learn from a source task to a target task, but using some intermediate task. This is what it's called curriculum learning. And I just want to stress from this work, very interesting work, which was published in 2021, that they said that distance between tasks is not symmetrical. For instance, if you have learned to recognize CIFAR10 images, it's more difficult. It's more easy to solve animals. To recognize animals, and if you start from animals to solve the CIFAR10 images, and even more than that, of course it depends on the hypothesis space that you have. For instance, if you have an 8-layer convolution neural network, which is much simpler than that one, then the distance is it's higher than here. Okay, it's much easier to do transfer learning if you have a large neural network than if you have a small one. Okay, I skip that because otherwise. So it is an interesting work. It is still a crude way. I have not had time to explain you how they devise their curriculum learning problem, but it's limited because it is the same input and same output space between the source and the target, and we have the same hypothesis space. Now, the question is, what if the space of task is not continuous? So I will present you now a new algorithm, a new way of looking at transfer learning, which is different from the three families that you presented. It's not model-based, it's not feature-based, it's not instance-based, it's something else. So, and it's called transboost. So, and also we will see that when looking at this type of algorithm, we will go back to the guarantees and the ingredients that we are expecting to play a role in transfer learning. Okay, so first of all, let's look at a task that I assume that most of you have some course on artificial intelligence, and if that was the case, you saw you had courses on game playing. And so you know minimax, alpha, beta, and that kind of algorithm. So in game playing, you have that kind of problem. You are here, you don't know what kind of move you should do. And in order to solve that problem, well, you go further down in the tree of possibilities, and then you have an evaluation function here which is more informed than that one. And so you go there, you query those information, those evaluation functions here, and then you go back by combining those evaluations to have a better one here. All right? So, so this is what I said. So you query experts that have more information about the task, and then you combine them back. And so, in a way, you could look at that like a transfer learning task. You have the source task here. You have a good hypothesis here. You don't know how to solve that task here. And the problem is, and you could solve this problem by querying those evaluation functions here, and then combining their answers. Okay? Okay. Can we do the same, as it is a kind of transfer here, for transfer learning? Can we do the same as game playing? Okay. Maybe, I don't know if you know about boosting, I suppose so. Yeah. Okay, so in boosting, you have your training data, and what you do is you learn what is called weak classifier. So a weak classifier is just better than random, okay? So you have an initial distribution on your data, you learn a weak classifier, you modify your distribution here, in order to have this hypothesis not better than random on this new distribution, then you learn a new classifier, a weak classifier, and you go on that way as many times as you want. And then at the end, you have a way to weight all those weak classifiers. I won't enter the detail. And then your overall hypothesis is just the sign, if you have only two classes, the sign of the weighted answers of your weak hypothesis. Okay? Now, can we do that for transfer learning? Could we, in a way, have weak something in order to do the same thing for transfer learning? This is what I devised with the transboost. The idea is the following one. So you have the target domain on the left and your source domain on the right. On the source domain, you have your hypothesis. Note that here I don't have any information about the source data. Okay? I suppose that the source data allowed me to learn a source hypothesis here. And now what I will do, I have some small training set. So I have to assume that I have some label data on the target task, but a small set of those label data. And what I will do is that I will learn weak projectors. A weak projector is something that allows me to go from the target data to the source domain. And if I have a better than random projector, is something that if I apply it to all my label data here, so I will have some projections here. I have something which is better than random. Okay, so that, for instance, this data, which I know, for instance, that it is plus, if I project it here with n projectors, overall, I will have a good answer. It is on the plus side of HS, for instance. So what I will do is that for each the training examples in the target data, I will see if my weak projector combined with HS is better than random. If it is the case, I keep it. And then I reweight my training data here, exactly like in boosting. That is, all the data that have been well classified have a smaller weight, and all the data points that have been badly classified have a larger weight. And I go again, I look at the next weak projector, and I do that as many times as I want. So at the end, okay, so this is, at the end I will have something like that, which you see, the projector allows me to transform target examples into examples that can be considered by the source hypothesis. And for each target example that I want to classify, I use the projectors that I have learned. I use a source hypothesis, which have been weighted exactly like in boosting, and it allows me to have the answer on the target side. Okay. So I have the algorithm is very, very simple because in fact it is a boosting algorithm just transformed in some very simple way. And if we do that, we have, I will show you, something which is quite interesting, quite performant. So what we did as a first experiment is, okay, just we had some control data. So here you have two time series. You have two families of time series. Some of them, oops, excuse me. Some of them have a positive slope here, which is a positive class. If you have a negative slope, you have in the negative class, and you have for the different classes, for the two classes, you have different shapes, and you have some noise factor here. So as you see, if you have very little data here, so this is like a time series. If you have little data, it's very difficult to distinguish between the two classes. If you have more data, of course, it's much more easy. So what we will do here is to play on the slope If the slope is high, of course, it's easy. It's an easy task. If the slope is small, it's difficult. And the noise factor also plays a role. And now, what is the source hypothesis here? My source hypothesis is an hypothesis which has been learned on the whole training set. Okay? I mean, on the whole time series. That is, the source hypothesis is good because it has a lot of information, all right? And now my target will be a limited time series with much less data. And the problem is, can I, thanks to transfer learning, can I still have a good performance when I have very little data points using an hypothesis that has been learned on the complete data set, on complete time series, I mean. Okay, if we look, so, okay, we have also to of course, to define what is the space of projectors. So here, in those experiments, we used inch functions, which are just something like so you have your previous time series, and then you continue it using just those very simple inch functions. Okay, so you have two parameters here, the angles, plus one here and one here. So you have 4 parameters. We have a limited set of projectors, and we will keep projectors that allow us to have a better than random classification on the target data. All right? So if we do that, so here is my source hypothesis with a very, very good performance. Here I have my target data only. If I train something on those data, as you see, the performance is very bad. So if you go down, it's easier because the length of the time series is longer, okay? So it's easier when you go down. It's easier also because the slope here is increasing, all right? So as you see, it's a very difficult task on the training, on the target data. But now if you look at transboost, look at the difference. I have very good performance, even though my performance on the training data was very bad. Okay, so I already have a jump of performance when using transboost. Okay, so as you see, so here it's for instance, here it's difficult. It's difficult for everyone because you have a very small amount of data, and you have a very small slope. Here it's easy. It's more easy for everyone because the slope is much higher. Anyway, so I just want to tell you that transboost on those control data is a very, very good algorithm. So now, if you look also at the very classical half-moon problem, where you train your data on this data set, and then you have this kind of data set, this is the best competitive algorithm, and this is our, as you see, our decision function is much better. And we did also additional experiments on images. So in images, suppose that you are trained on those kind of data here, and you are not tested on data images with low resolution, all right? So you don't have the same input space. Or you have been trained on recognizing 0 from 1s, and then you are tested on 7, I mean your target data is to distinguish between the 7 and the 8. So when we did that, and we did also something different, for instance, yeah, we did also, it was very amusing, at Telecom, actually, with students from Telecom. Our task A, our source data was natural images like that, and then we trained using transboost or recognizing system about those data here, and we got approximately perfect performance. And I don't know any other system that is able to do that. So, okay. So what we did, what kind of projector did we use? Of course, for those tasks, we used first layers. So we had, this is the standard transfer. So standard transfer, you freeze the first layers and use them here, and then you learn that. In our approach, it's just exactly the reverse. We keep that, the higher layers of our neural network, which was trained on the source task, and we train the first layer or the 2 first layers only. Okay, so this is a weak projector, which allows you to go from the source data, for instance, your cat, your natural cat, to your comic cat. And then, as soon as you have a layer here that allows you to be better than random, you freeze everything, you keep it, and then you do it again with a second thing and so on. Usually, we do that for 10 to 50 steps like that. And using that, we have very good performance. Okay. Okay, so in a way, you have your space of tasks here, and exactly like in tracking, for each task, you have a weight on the projectors here. So we have a kind of embedding, which is a space of projectors, and we have weighted projectors, and those weights depends on the task that you are looking at. Okay, so I suppose, but I'm not sure about that, that if we went from one task to another using different paths, we should get different results here, which is we should expect to have path dependence, but that I'm not sure. Okay, now let's go back to our original questions about the ingredients that play a role in transfer learning, in the kind of guarantees that we can have. We did something very strange. Actually, we did it by error. But at one time, we picked a source hypothesis which was not better than random. Okay, so for instance, on those time series, the source hypothesis was not good at all. But we did the whole thing, and we managed to get. Oops, sorry. Yeah. Okay, and we managed to get those very good results, as you see here. Even though the source hypothesis is like that. So this is quite astonishing, as I can see, because we don't expect that at all. I mean, for us, it was a complete surprise. It means that you can use a source hypothesis, which is not good at all on your source task, and it can help you on your target task. Why not, after all? Because what we do is just to use this source hypothesis in order to find good projectors. If we find better than random projectors, we do as a boosting. We have weak classifiers, actually. They use a bad source hypothesis, but after all, who cares, in a way? So of course, it is a little bit surprising because the quality of the source hypothesis plays no role. The proximity of the source on target data plays no role because I'm not using at all the source data here. And still, of course, there is this question: no condition on the source hypothesis. That seems very strange. Because if we look at transfer learning ourselves, well, usually we have an idea about what is easy to transfer and what is not. So how come intuitively for us there are easy transfer on some that are difficult, and especially if the source hypothesis is like random one, we will say it's a bad transfer learning task, and still we have that kind of results. So for me, yeah, transfer acts as a bias, and HS is a strong ingredient in that bias. And if the source hypothesis is well chosen, I mean, well, it is useful, but of course it seems random on your source task, but it is useful. Well, it has a good bias. But after all, if you look at classical supervised learning, very often we choose bias, but we don't know exactly why they're good. Sometimes, of course, you say, my hypothesis should be very sparse. Okay, and you know your biologist said to you, a small number of genes play a role, so you should look at sparse hypothesis. But very often you don't know, actually. And it is exactly the same here. Sometimes you have good bias, and you don't know exactly why, but it is good, and sometimes it's not. Okay, so now the learning problems now becomes the problem of choosing a good set of weak projectors. And I can say to you that there are theoretical guarantees. I don't have much time to look about that, but we have also guarantees like that where you see the Vapnik dimensions of your HS ROM pi is the capacity that is important now. So I don't have time to go over that. And so my conclusion is, first of all, that transfer learning so far is mostly heuristical approaches. I think that parallel transport is a natural way for looking at transfer learning. So we should consider that more. The covariant derivative is then a measure of difference. The problem is how to compute it. It's easy to compute it, or at least you can compute it on a continuous surface. It's not easy at all when you have something which is discontinuous, like in machine learning very often. We have pioneering works in computer vision. If the source and target domains are different, I don't know how to do it. I just showed you transboost, which for me is some way of doing that, but I'm not sure. Transfer learning is path dependent in general, and we should study that because it's really related to curriculum learning, to what I'm doing when I am a professor. I'm trying to organize the materials in a good way. So we should do that also for our machines. But it is still a wide open research question. And then just to conclude this time for good, theoretical guarantees for transfer learning do not necessarily depend on the performance of source hypothesis, but they involve the capacity of the space of transformation. Okay, with this, I thank you for your attention.
Thank you for the talk. We have time for questions.
I don't understand exactly the link between the parallel transport and the transboost.
Yeah, I agree with you. I'm not sure either. Because, yeah, I agree with you. Parallel transport, for me, it's really something. I mean, if you do transfer learning, it seems obvious to me that it should be related to parallel transport. That is, really, you have your hypothesis in some space, and you want to transport it parallel to itself to a new task. Okay. Now, I agree with you. When I was preparing for that talk, I was wondering what I would present. And I am very fan about transboost, that I find a very powerful algorithm. I would like to be able to show that it is a kind of parallel transport when you have when you don't have the same space. But of course, yeah, I don't have. I cannot assure you that it is a good way to do it. I don't think so, actually. No.
In your examples, you contrasted the fact that traditional approach was to change the last layer, while you look at
the first one.
The first one, but in fact, in the same intellectual framework, you could actually move an arbitrary layer in the middle. So you studied if...
no, I haven't, but you're right, of course. I could. Well,
I mean, it conceptually doesn't change much. I think it's still in your framework. So.
Yeah, you're right. Yeah, kind of yeah, we could try that also. I was really inspired also by, a CEO, for instance, your chief officer, CEO, chief executive officer. You are supposed that if you have been good at selling cars, for instance, you should be good at selling, I don't know, perfumes. So you have the same kind of decision makers, and you just change the first layer. That is the kind of products that you are considering. And yeah, transfer learning, of course, very usually it is like that. It is not exactly what is done in the classical neural networks. It's the opposite. It is, you have your decision, you know how to take decisions, and now you have a new set of tasks, but you have the same kind of decision making that you do. So yeah, it was a kind of inspiration. I'm not claiming it was the only one, but in a way, I think that very often we have that kind of thing, that you're supposed to be intelligent, that is to know how to make decisions. And then you can adapt to different tasks. You learn to do that.
How can we combine curriculum learning, so the way to be able to present in a certain order the examples, and the transboost algorithm, which is a way to wait, but also we can imagine offering the subset of examples through the combination of recurrence.
Yeah, I find that this work here, I find it very interesting. They're trying to compute a curriculum, and they do it by looking at the distance. Well, Yeah, at the same time, they move the training data on the hypothesis, and so they try to have training data that is easy to learn from the current hypothesis, and then they adapt the current hypothesis to the new training data and so on. And I guess this is related to what you say in a way. I mean, I would like to do the same with transboost, but again, I don't have the answer right now.
Yeah. I think even for the boosting algorithm, it can be a way to.
Yeah, but I'm like you. I have many questions stemming from that kind of work. Yeah.
Just one question is, how do you optimize the projection or the alpha parameter in the target domain?
We don't optimize it at all. We really do that. Sorry. We really do that like in boosting. That is. If I go back to that, yeah, you see, you have your small training set here, and then for each one of them, you learn a projection. So you have a P1, for instance. So each of these data is projected here. And you look, you see if, using that projection, and using H of S, you have a better than random guessing of the classes of your training data. If it's better, you keep it. And then you modify the weights of your data, and you learn a second projector and so on.
Okay. And the alpha?
And the alpha are learned exactly like in boosting. That is, if your weak learner is strong, you have a larger alpha than if it's very weak.
On the source domain?
On the training data also. Really, in fact, we are doing boosting. It's really boosting on this, except that you are using that kind of very strange thing, which is weak learners that use the source hypothesis. But otherwise, it's like boosting. And actually, when I first tried to publish that, there was a reviewer who said it's too simple. It's not worth publishing. So, yeah.
Regarding the parallel transport, if we have to do an analogy with a vector that we transport parallel to himself, like the source hypothesis, it is this vector that we want to transport. Mm-hmm. So composing to compose the function together, the way of transporting.
Mm-hmm. Yeah, exactly that. Yeah, but I don't do it continuously. Here I do it in one step. That's why I can't claim that it is a parallel transport, because parallel transport is really like you have to have a derivative. If you don't have a derivative, and actually you're not able to define what is parallel transport.
But is there any formal framework to embed these things? Like
it's a fiber bundle. I mean, if you look at mathematics, it's fiber bundle class of problems, and relativity, general relativity, is a kind of fiber bundles where your fiber is just the tangent space that you are considering. But here, the fiber, which would be the space, the hypothesis space, and so you have your hypothesis in the fiber, and it's changing as you change your task. And you could look at it like a parallel transport. But it's very difficult because the space of task, except for computer vision where it's more easy, it's not continuous usually, like here. And so how to define really properly parallel transport in that case, I don't know how to do that. I mean, it would be very interesting if some of you could do that.
Yeah. So here's a follow-up question. So you show the path, and I think people propose to use a Wasserstein transport.
Mm-hmm.
In this case, you have a well-defined notion of parallel transport.
I don't know. I don't know if Wasserstein distance can be considered as parallel transport.
No, but you have a path of distribution.
That's true. That's true.
But then, you have a path.
Mm-hmm.
Can you define a well-defined notion of parallel transport along that path?
I don't know. I mean, I'm really working on that actually right now, and I cannot tell you really a definite answer on this. But yeah, I think between optimal transport and parallel transport, there should be something. Yeah.
Do you have a published algorithm?
Oh yes, yes, of course, it's published.
On GitHub?
Yeah, it's if you go on my site, of my website, on Google Scholar also, yeah, you'll find it.
Okay, thanks again.
Thank you all.